In this example, we're asked to determine whether this series, the sum from n equals 1 to infinity, negative 1 to the n squared over n squared plus n plus 1, is convergent or divergent. This section of the notes is about the alternating series test, and we notice that this series is indeed an alternating series. The key indicator here is this negative 1 to the n. This gives us the idea that this could be an alternating series, but it's not enough to justify that, yeah, indeed it is an alternating series. Instead, we also have to check two facts. Those two facts are that n squared over n squared plus n plus 1. So the general term, taking away the alternating portion here, the negative 1 to the n, this portion should be, so this is a question, but is this portion both positive and decreasing? And if so, the alternating series test applies. This is, of course, positive because n squared plus n plus 1 is always going to be positive when n is greater than 1 or greater than or equal to 1. So n squared over n squared plus n plus 1 is greater than 0 for all n. Alright, so we've got positive, and it's decreasing because as n increases, n squared plus n plus 1 is always larger than n. Alright, so n squared is always less than n squared plus n plus 1 for, again, n greater than or equal to 1. Here I wrote for all n. I mean greater than or equal to 1 for that as well. And so these are the criteria that tell us that we are allowed to use the alternating series test. Remember, this is not the alternating series test itself. Okay, so the next step is to take the limit. Okay, so the alternating series test says provided these two criteria are met, then we can take the limit of the positive portion of the alternating series, and the value of that limit will tell us whether the series converges or diverges. So the last thing we have to do is then compute the limit, n squared over n squared plus 1. And remember that when talking about sequences, the only kind of limit that makes sense, and I frequently leave this off because it's the only limit that makes sense, but the only limit that makes sense is the limit as n approaches infinity. Okay, and as n approaches infinity here, one of the methods for computing this is to multiply through both the top and the bottom of this limit by the 1 over the highest power of n. And you're allowed to do this in a limit because, just by limit rules from Calc 1. So this limit is now the limit as n approaches infinity of 1 over 1 plus 1 over n plus 1 over n squared. And of course, at this point, these two terms, 1 over n and 1 over n squared, as n becomes very large, these two approach 0. And the result is that the limit equals 1. Okay, now what does this tell us? By the alternating series test, which I'll just abbreviate AST, this limit is not 0. So the limit of the b sub n in this case is not 0, and therefore this series is divergent. Okay, so the series n equals 1, the series in question, n equals 1 to infinity, n squared over n squared plus n plus 1, this is alternating, negative 1 to the n. This series is divergent. Okay, it does not converge, it's divergent. Okay, so at this point you're probably thinking, okay, well, that's great, but couldn't I have just used the test for divergence? Because look at this, if this limit is 1, then the limit of the alternating series is non-existent, because it's saying that as n becomes very large, the values of the terms of the series, so the values in the sequence, these are alternating between 1, negative 1, 1, negative 1. Okay, and so the limit, it turns out, the limit as n approaches infinity, negative 1 to the n squared over n squared plus n plus 1, this does not exist, and if it does not exist, then it does not equal 0, and so actually the test for divergence applies to this series. Okay, so either way is fine. You get the same result. The series is divergent. This alternating series is divergent.